Dear friends, myself Dr. Ganesh ALAWANDI, Assistant Professor, STM Degree College, Honavar. Today I am going to discuss about the applications of phenols. Phenols serves as a useful intermediates in the many organic synthesis. Now we will see one by one here. That is the coal-based reaction. So when sodium phenate treated with carbon dioxide gas at 125 degree centigrade under 6 atmospheric pressure followed by acidic hydrolysis to yield the salicylic acid here. So now we will see the reaction. So this is the reaction. So this is sodium phenate. This is the structure 1. When the sodium phenate is treated with carbon dioxide at 125 degree centigrade and under 6 atmospheric pressure, so results in the formation of sodium salt of this salicylic acid. So the hydrolysis of this is the acid hydrolysis of this sodium salt of salicylic acid results in the formation of salicylic acid. That is the structure 3. So this is the salicylic acid here. So this is the product of coal-based reaction. Now we will see the mechanism of this reaction. So this is the mechanism here. So structure 1, this is phenate anion. So here we have the phenoxide anion. So here the moment of electrons. So here this position 2 becomes the electron rich here. So here we have the electrons. So this position is electron rich center. So in the carbon dioxide we have the carbon is flanked by 2 double bond over here. So 2 oxygens are held by double bond here. So we have the 2 double bonds. So since the oxygen is more electronegative than the carbon, so these bonding electrons will move towards the oxygen. So here oxygen becomes the electron rich, that is the electrons towards the oxygen and leaving this carbon electron deficient here. So carbon gets the positive charge here. So this is the electron deficient. So carbon is electron deficient. So now we have the electron deficient carbon and here we have the electron rich center. So electron rich center that attacks this carbon here, that is the electron deficient carbon. So forms the intermediate 4. So there is a loss of proton from the intermediate 4. So it means there is a aromatization of this intermediate will takes place. So we will get the sulfide anion. That is the structure 5. So this is the anion here. So once this sulfide anion, that is the structure 5, that is acid hydrolysis or acidification of this compound 5, we will get the salicylic acid. So this is the structure 6, salicylic acid. So this salicylic acid is the product of this coal-based reaction. Next we will move to the Rhimatimate reaction. So when phenol is treated with chloroform in the presence of aqueous sodium hydroxide followed by acid hydrolysis to yield sulfalaldehyde. So in this reaction, if we use carbon tetrachloride instead of chloroform, the salicylic acid would be the formed product. So it means, so in case if you are using the chloroform, the product will be the sulfalaldehyde. Suppose if you are using the carbon tetrachloride, the product will be salicylic acid. Now we will see the reaction. So here we have the phenol, that is the structure 1. When this phenol is reacts with this chloroform in the presence of aqueous sodium hydroxide solution, so results in the formation of sodium salt of sulfalaldehyde. So this is the structure 2. We will get the sodium salt of this sulfalaldehyde. So in the next step, there is a acidification of the sodium salt of sulsaldehyde. Finally, we will get the sulsaldehyde. So this is the structure 3. So here in this reaction, we are using the chloroform. So product will be sulsaldehyde. Suppose in place of this chloroform, if you are using the carbon tetrachloride, the product will be, that is, salicylic acid. Next we will see one by one here. So that is the mechanism. So in the mechanism, there is a generation of dichlorocarbonyl, that is the reactive species. So this is the chloroform. So in the chloroform, we have the 1H. So when this is treated with sodium hydroxide solution, that is the base. So there is a that picks up the proton here. So that forms like this. So these bonding electrons are with the carbon itself. There is a loss of H plus here from the chloroform. So in the next step, there is a loss of chlorine atom. So one chlorine atom will be lost here. So there is a formation of 2 electrons. This is the electron deficient. So this is electrophile here. So this is more reactive. So that is the step 1, that is the generation of dichlorocarbon. So this is the dichlorocarbon. So this is reactive. Okay. So now there is a formation of electrophile here. So in the next step, that is the attack of electrophile. So here we have the sodium phenoxide, that is the phenoxide anion. So there is a movement of electrons. So this second position becomes the electron rich. So this is the dichlorocarbon. So we have the electron deficient carbon here. So this is the electron rich. So this attacks the carbon here. So we will get the intermediate 4 here. So in the intermediate 4, the carbon which picks up the proton from the water, so that forms the structure 5 here. So this is the intermediate 5. In the intermediate 5, there is a loss of proton. So it means there is a aromatization of this benzene ring will takes place. So results in the formation of, this is the structure 6. So in this structure 6, there are 2 chlorine atoms here. So when this is treated with sodium hydroxide, there is a formation of dihydroxy compound. So that is the structure 7. So there is a loss of 2 chlorine atoms from the structure 6, results in the formation of 2 hydroxyl groups here in the structure 7. So in the next step, there is a loss of water from the structure 7. So here there is a loss of water. So we will get the sodium salt of this sulsaldehyde. So this is the structure 8. So in the next step, there is a acidification of this structure 8. So we will get the sulsaldehyde. So this is the structure 9. Suppose if we are using the chloroform, we will end up with the sulsaldehyde. So next we will move to the method 2. That is the phenol. So here we are using the phenol. When this phenol is treated with carbon tetrachloride, so this carbon is attached to 4 chlorine atoms here. So in the presence of aqueous NaOH, we will get the, this is intermediate 2, that is the sodium salt of this salicylic acid. So when this is acidified, we will get the salicylic acid. So structure 3 is the salicylic acid. Now we will see the mechanism of this reaction. So here we have the phenoxide anion. So there is a movement of electrons. So second position becomes the electron rich here. So in the carbon tetrachloride, that is the structure 3. So carbon is bonded to 4 chlorine atoms. So this is the phenol is the electron rich. So this is the electron deficient, that is attached to 4 chlorine atoms here. So this attacks the carbon here. So that forms the intermediate 4 here. So from the intermediate 4, there is a loss of proton here. So it means there is a aromatization of this benzene ring will takes place. So that forms the structure 5. In the structure 5, there are 3 chlorine atoms. So there are 3 chlorine atoms. When this is treated with sodium hydroxide, so one of the chlorine atom will be replaced by OH here. Okay, that becomes the OH. So this is the structure 6. So from the structure 6, the OH molecule which loses the proton here, so there is a formation of double bond here. So we'll get the acyl chloride. So this is acid chloride. Even we can call it as a acyl chloride. So in the acyl chloride, there is a polarization of this C double bond will takes place. So once there is a polarization of this C double bond O, so this carbon will be the electron deficient. So OH minus, which is present in the reaction mixture, so that attacks this carbon deficient, this electron deficient carbon, so that forms the hydroxy compound here. So this 2, that is O minus, OH and 1 Cl will be there. So this compound, that is the structure A, that is unstable here. So the electrons on the oxygen, they comes here. So there is a loss of 1 chlorine atom. So that forms the sodium salt of salicylic acid here. So this is the sodium salt of, this is salicylic acid part. So in the structure 9, there is a transfer of proton from COS to, that is ONA will takes place. So that forms the structure 10. Here OH. Then this COH of this structure 9 becomes the COONA, that is the sodium salt. So when this is acidification, we will get the structures 11, that is the salicylic acid. So in this reaction, if you are using the chloroform, we will get the salsaldehyde. Suppose if you use chloroform, suppose in this reaction, if you are using the chloroform, the product will be the salsalaldehyde. In case of chloroform, if you are using the carbon tetrachloride, the product will be the salicylic acid. So next we will move to the another reaction, that is Gattermann-Koch synthesis. So in this reaction, when phenol is treated with hydrogen cyanide and hydrochloric acid in the presence of zinc chloride to yield the salsalaldehyde. Now we will see the reaction. So here we have the phenol. When this phenol is treated with HCN and HCl. So this is the hydrochloric acid. So this is the hydrogen cyanide. When this phenol is treated with these two in the presence of zinc chloride, so we will get the salsalaldehyde. So structure 2, that is the salsalaldehyde. Now we will move to the mechanism. So step 1, that involves the generation of electrophile. So that is electrophile, that is the reactive species here. So here structure 1, that is the hydrogen cyanide. So carbon triple bond N. So in the hydrogen cyanide, that is carbon and nitrogen is attached by triple bond here. So in the reaction we have the acid here, that is the HCl. So that is the protonation of this nitrogen will take place here. So that forms the structure 2. So this is the intermediate here. So now we have positive charge on the nitrogen. So this is balanced by ZnCl3 minus. Okay. So in the next step, there is a movement of, that is a rearrangement of this electrons will take place. So this triple bond electrons are moves towards the nitrogen, so leaving this carbon electron deficient. Okay, so this is the structure 4. So here we have this C plus, so this is the electron deficient, so this is double bond NH, so 2 electrons on the nitrogen. So this is the electrophile here now. So this structure 4, that is the electrophile, which is reactive species. In the next step, that is the attack of electrophile. Here we have the phenol, movement of electrons. So here second position becomes the electron rich here. So from the earlier step, that is the structure 4, we have the electron deficient species, that is the carbon is electron deficient here. So this electron rich that attacks the electron deficient, so that forms the intermediate 2 here. This is the intermediate 2. So from the intermediate 2, there is a loss of proton. It means there is a aromatization of this benzene ring will takes place here. So there is a formation of compound 3. So this is the compound 3. So here we have the C double bond N, so imine bond. So when this compound 3 that is treated with acid, there is a hydrolysis of this double bond N will takes place. So finally we will get the sulfonaldehyde. So this is the product of this Gattermann-Koch synthesis. Next we will move to the another reaction, that is the Claisian rearrangement. So in the Claisian rearrangement, when O-allyl ethers of phenol is heated about 20 degrees centigrade in the absence of catalyst. Absence of catalyst means we are not using any catalyst in this reaction. So this undergoes the rearrangement to yield the O-alkyl phenol. So when O-allyl ethers heated in the absence of catalyst, so there is a formation of ortho-allyl phenol. So this thermal rearrangement of allyl phenol ethering into ortho-allyl phenol is known as Claisian rearrangement. So when the O-allyl ethers are heated in the absence of catalyst, there is a formation of ortho-alkyl phenols. So this rearrangement is called Claisian rearrangement. Now we will see the reaction here. So this is the reaction. So this is O-allyl ether of phenol. So this is the structure 1 here. So when this is heated, here we are not using any catalyst here. So there is a rearrangement of this O-allyl ether will takes place. So here the formation of compound 2, that is the ortho-allyl phenol. So in the starting material, the carbon 1 which is attached to the oxygen, that becomes the terminal carbon of this product here. Okay. Now we will see the mechanism. So here O-allyl ether of phenol, this is the oxygen is attached to the allyl group. Okay, this is the ether. So because this oxygen is bonded to 2 groups here, so that is the phenol, that is the ether. So when that is heated, when thermal energy is supplied here, so that becomes the intermediate here. So there is a loss of proton and there is a formation of ortho-allyl phenol. So here the carbon atom which is attached to oxygen, that becomes the terminal carbon atom in the product. So the above reaction is evidenced by C13 labeled carbon here. So now we will move to the next reaction, that is the Price rearrangement. So when phenolic esters treated with anhydrous aluminum chloride yield orthohydroxyacetophenol. So this is the reaction. Here this is the phenolic ester. So this is the ester group. This is phenolic ester structure 1. When this is heated in the presence of anhydrous AlCl3, that is the aluminum trichloride. So we will get the orthohydroxyacetophenol as well as para-hydroxyacetophenol. So this is orthohydroxyacetophenol and para-hydroxyacetophenol. These are the products of this price rearrangement. The formation of ortho and para isomers is mainly depend on the temperature of the reaction. At low temperature, the formation of ortho product is dominant, and at higher temperature, the formation of para product is dominant. So, at the lower temperature, the dominant product will be the ortho isomer, and para isomer will be the less percentage. So, at higher temperature, the orthohydroxyacetophenol percentage is less. So, the percentage of para-hydroxy isomer is more here. So, this reaction is temperature dependent here. So, now we will see the mechanism of this reaction. So, this is the phenolic ester. So, here we have a oxygen. So, we have AlCl3, that is aluminum trichloride. So, here we have a lone pair of electrons. So, there is a formation of this AlCl3 bond here. So, once the oxygen becomes the electron, that is the positive charge on the oxygen. So, this becomes the unstable here. So, this try to lose some group here. So, this acetyl group is, that is the easily leaving group. So, here the bonding electrons are retained by this oxygen and leaving this acyl cation is releasing here. Okay, so that once this acyl cation is released, so this forms the structure 3 here. Oh, okay, this is the structure 3. As we know that the position 2 of the phenol is electron rich here. So this acyl cation is released from the structure 2 here, which is present in the reaction. So which attacks the position 2 of the phenol. So we will get the intermediate 4 here. So this is the intermediate 4. So in the intermediate 4, there is a loss of proton, means there is a aromatization of this benzene ring will take place. So we will get the structure 5 here. So when the structure 5 is acidified here, so we will get the orthohydroxyacetophenol. This is the structure 6. So now we will move to the next reaction, that is the Rearrangement reaction. So in the Rearrangement reaction, when phenol is treated with formaldehyde, so this reaction is proceeds in acidic condition as well as the basic condition. So when this phenol is treated with formaldehyde, we will get the phenyl 2-methanol. So this is the structure 2. Here we will get the phenyl 2-methanol. So when this phenyl 2-methanol treated with another molecule of this phenol, so we will get the novolac. That is the structure 3. So this is the novolac. So when this novolac heated with this formaldehyde, so there is a cross linking of these phenols will take place. So that forms the polymer. So that polymer name is, that is the buckyl. This is the structure 4. Dear friends, with this I have completed that is Kolbe's reaction and Rhimatimate reaction, Gutterman synthesis, Claisian rearrangement, price migration, and the Rearrangement reaction. So with this is the completion of application of these phenols.